The next problem that we'll be going over is problem number 8 from the review. Problem number 8. So please be on problem 8 from the review. Let's read first. It says, a light in a lighthouse 1 kilometer offshore from a straight shoreline is rotating at 2 revolutions per minute. How fast is the beam of light moving along the shoreline when it passes the point 1/2 a kilometer from the point opposite the lighthouse? So, if we draw a picture, we draw a straight shoreline, we draw this lighthouse. This is a bird's eye view. The lighthouse is shining on the shore or around into the water, and it is 1 kilometer offshore. Now, the lighthouse's beam is rotating, so if it is shining, it's rotating around. So, at some point, it is going to hit the shoreline, and let's say it is moving along the shoreline. So, let's say we have this distance x, that the beam of light is from the point directly across from the lighthouse. So, if x is this distance and the beam is moving, then there is a dx dt. Now, if the beam is moving, that means from the lighthouse's perspective, there is an angle that is created. Call that theta. And since that is changing, there is a d theta dt. So now, you are told that, let's see, going back up, it is rotating at 2 revolutions per minute. So that is the d theta dt. So 2 revolutions per minute. Now, what does a revolution mean? Revolution means that it is spinning around 1 full time. So we actually need to turn that into an angular measurement. So 2 revolutions per minute. Well, how do you change that? If you want to convert revolutions per minute into an angle, you would have to multiply by 2 pi radians per 1 revolution. So revolutions would reduce, leaving you with 2 pi radians per minute in 1 revolution. So if you have 2 revolutions per minute, that means you have 4 pi radians per minute. Now, remember, radians is an important angle measurement because it is directly connected to distance. So now, if we look at our problem, how are x and theta related? Well, they're related by a tangent ratio, right? Tangent of theta would be equal to x over 1, or just x. So tangent of theta equals just x. Now, once I write my equation, I'm ready to take the derivative implicitly with respect to time. The derivative of tangent theta with respect to time would be secant squared theta d theta dt. And the derivative of x with respect to time would be dx dt. Now, that is one way that we can approach the problem. But if I am trying to find dx dt, so find dx dt, when, what are we told? Well, it says when it passes a point 1/2 a kilometer from the point opposite the lighthouse. So that would mean that x is 1/2. So if I'm trying to solve for dx dt when x is 1/2, I look at my problem, I would still need to know theta. So tangent of theta is 1/2. But in terms of a by hand question, I don't know the value of theta when tangent is 1/2, not off the top of my head. So in a non-calculator setting, we can actually approach this problem from a different perspective. If tangent of theta equals x, then I could rewrite it as theta equals the inverse tangent of x. Now, why would this be beneficial? Because the derivative of theta, yes, is d theta dt. But now the derivative of tangent inverse of x, if you remember your rule, is 1 over x squared plus 1 times dx dt. Now, why would we prefer this second one over the first one? Because if we want to solve for dx dt, now I only have x and d theta dt, so I no longer have a need for theta. So if we continue on the right side, d theta dt is 4 pi radians per minute equals 1 over x, which is 1/2, squared plus 1. dx dt. So now 1/2 squared is 1/4. So I have 1/4 plus 1, which is 5/4. So I have 1 over 5/4 times dx dt equals 4 pi. So now, if I want to divide by 5/4, which would be the same as multiplying by, I'm dividing by 1 over 5/4, which is the same as multiplying by 5/4. So 5/4 times 4 pi equals dx dt. And so if I reduce, I get 5 pi. dx dt is 5 pi. Now what would the units be? Well, because we used radians per minute, then we can convert that directly to our linear measurement of kilometers. So 5 pi kilometers per minute.